Good afternoon and welcome to this theme session on novel approaches to the detection of domain generation algorithm related threats, DGAs. As you can see on the slide, this webinar is a joint production of two European innovation projects, both of which focus on the automation of cybersecurity operations, and both of which have chosen to address the DGA problem as part of their work. One is the SOCCRATES project that is building an automation platform for SOC and CCERT operations, elaborate automation. The other is SAPPAN, which is pursuing an information sharing platform for incident response, incident recovery, while preserving confidentiality and user privacy. You'll hear more about these projects as we go. We have the projects managers in to give an overview. My name is Richard Kerkdijk. I'm a senior consultant here at TNO in the area of cybersecurity. I'm involved in the SOCCRATES project and I'll be moderating today's session. So I'll be brief, but let me start with some practical remarks. First off, if you have any questions, which is conceivable, and you'd like to raise your questions, please do so via the chat. We'll not be opening up your microphones, but the chat is open to any and all input and ideas that you would like to put forward or things that you would like to clarify us further. So please place that in the chat and we'll monitor what's happening there. We'll take time at the end to answer your questions. If necessary, we might also pause somewhere in between if there's an urgent question. But for the most part, we'll save the questions until last. I'm also going to emphasize that you are very welcome to write everything down, take as many screenshots as you like, but we will be sharing a video of today's webinar, plus all the material that you see on our websites shortly after this session. So there is no need to write everything down. We'll get all the material out to you when all of this is done. So today's program, what we'll do is we'll start with a very brief overview of both projects from which all of this work has stemmed. So the SAPPAN project and the SOCCRATES projects. And that will be followed by an explanation of domain generation algorithms and why they are such a relevant problem for us to pursue in our work. And then you will hear about novel concepts for detecting DGAs and addressing DGAs that we have under development. And also about the impact that both projects have achieved thus far, both in an academic and innovation sense, but also in real life operations. And in addition, you'll see a live demonstration of one of the solutions that is being built, which is what we call the DGA Detective. If all of that goes well, we hope to have 10 minutes left at the end to address your questions, as mentioned before. So before we dig into the actual content, I'd like to introduce you to the presenters we have today. And perhaps I should start with the project coordinator. So perhaps Avi, you could introduce yourself briefly.
Hi. Can you hear me?
Yeah.
Okay, yeah. So hello, everyone. So my name is Avi Karshamandal. So I'm a senior researcher at founder for FIT and currently coordinating the SAPPAN project. So yeah, so I'll be very happy to give you a brief introduction to SAPPAN project today. So yeah, back to Richard.
All right. Reiner?
Yeah, thank you, Richard. I'm a colleague of Richard at TNO. I'm the coordinator of SOCCRATES, and I'm also a senior cybersecurity consultant and project manager.
Right, and then we'll move over to the content experts. First and foremost, Irina.
Yes, hello, everyone. My name is Irina Kiskop. I work together with Richard and Reiner at TNO. I'm a scientist, and I'm active in the SOCCRATES project, doing work on DGA detection. That's what I'm going to present a bit later.
All right, thank you, Irina. Piotr?
Hello, my name is Piotr Kijewski. I'm from the Shadow Server Foundation, where I also run quite a lot of large-scale data collection and sharing projects, and also currently act as the foundation CEO. And Shadow Server is involved in the DGA detection problem by essentially applying the methods developed for DGA detection to its large-scale sandbox data collection.
All right. Thank you, Piotr. And then finally we have Arthur.
Yes, hi. I'm Arthur Drischel. I'm a researcher at the IT Security Research Group at RWTH Aachen University in Germany. And in the SAPPAN project, I'm working on intrusion detection and in particular on DGA detection.
All right. So there you have our lineup of presenters for today. And I guess this is a moment where I stop talking and hand over to our first presenter, which is Avi, who will share a bit about the SAPPAN project.
My screen. Yeah, okay. So hello and welcome. So the SAPPAN project, it's an acronym, and the full form is Sharing and Automation for Privacy Preserving Attack Neutralization. So it's I'm giving just a brief overview of the project, some administrative details here. So it was accepted in SUICT call from 2018, Dynamic Countering of Cyber Attacks. And the scope is cyber attacks management and advanced response and recovery. So the SOCCRATES project was also part of this same call. So basically, we have a lot of common research areas. So the timeline was, it was started at in the month of May 2019, and it will continue until April 2022. So it's the last year of our project. And yeah, so we have a overall budget around over a little bit more than 4.5 million. So the project in general, some of the highlights are we want to support human operator, the CSRIT members to find optimal response and to recover from the cyber attacks. And in the project, we are developing a privacy preserving threat intelligence sharing platform among an organization such that they can have an effective response and recovery. And we're looking from two approaches. One is a local approach, so one organization can do different stuff, such as incident handling to detection and handling together, and also at the federated level where they could do it at a collaborative fashion. So also we are working on some visual and interactive support for the SOC operators. And then we have some scalability improvement that we are looking at for data processing for intrusion detection. And finally, we are also working on response recommendation and automation for the SOC operators, what they do. So just to give you a little bit of the consortium overview, so we have 8 partners. So Founder for Fit as we're the project coordinator, and we have 4 commercial partners, from HPE from Ireland, SESNet from Czech Republic, F-Secure from Finland. Then we have DreamLab from Switzerland, and we have 3 academic partners from University of Stuttgart from Germany, Masaryk University from Czech Republic, and RWTH Aachen University from Germany. So this is a little bit of an overview of how SAPPAN data sharing approach, how it works. So we are focused. So we can think about a incident management lifecycle. So we have a detection and handling, and in incident detection, you have large scale data, cybersecurity data gathering, and then detection. So at local level, you can think of a organization is trying to improve their capacity, SME, or a millions in European mid-sized company. They're trying to improve their the detection capabilities, and on the other hand, it could be improved from on the sharing that different data, different detection modules, or playbooks, for example, and this could be done in a privacy preserving manner. And so also looking at the incident handling and the handling part, such as assessment and response actions, such as playbooks. So yeah, so one is we're looking from the local level, and one we are looking at federated, at collaborative level. And also privacy issues are has been taken care of while sharing the data. Then some of the highlights of SAPPAN innovation. So we've developed some machine learning based tools for attack detection and response. So Arthur will also present today some of the tools, DGA detection tools that have been developed in SAPPAN. And other than that, we are also worked on sharing threat intelligence between approaches for sharing threat intelligence in a privacy-preserving manner, and also visualization component for SOCs, and finally response recommendation and automation. Yeah, and thank you.
We are in the final year. We run until next August, till September 1st. We have around 10 partners, also from different sectors. So some industrial partners, a few universities. Shadow Server, already introduced by Piotr, is a threat intelligence provider. We have an MSSP, Mnemonic from Norway, and we have Vattenfall, the IT SOC of Vattenfall in Poland, as end users to do our pilots. So I think we have a very interesting consortium. And a few words to the background. So what we see, also already noticed by ENISA in 2017, that the balance between defenders and attacks is still not good. So there's, despite the increased defense levels and expenses, we cannot successfully defend ourselves against cyber attacks. And why is it? Well, we have an increasingly complex and dynamic ICT. The number and complexity of attacks is growing. Attacks get more automated, while we see in the SOCs that are currently there, the response is mainly human-centered. And also there's a shortage of cybersecurity staff. So this is why we have in SOCCRATES an objective to develop and implement a security automation decision platform. So to support the SOC operator and to enhance the effectiveness of the SOC and CSIRT operations in such security operating centers. Well, how does this look like? We have designed a modular platform where you can plug in different platforms with an orchestration integration engine in the middle where the workflow is defined. And we connect to existing security monitoring solutions, so we are not looking at greenfield. And we have different modules which do different which cover different aspects of security automation. Like underneath, we have the AI-based attack detection. We do infrastructure modeling, and based on the infrastructure modeling, we do attack defense graph analysis, and we define course of action to present to the operator. And we also do the same for business. So we have a business impact analyzer, response planner, business modeling logic. We do some automatic reconfiguration, not much, but we're starting to a little bit initial automatic reconfiguration. And we have a threat intelligence module. And all this is designed to provide the SOC analyst with situation awareness and option awareness, so he can make more defined choices. We will test this platform, which we currently are implementing in a few pilots. 2 main pilots will be conducted at Vattenfall Mnemonic, and Shadow Server provides the threat intelligence for those pilots. They will start in February. We already had a technical pilot in the beginning of this year, which provided us a lot of insight on what to do with the main pilot. So the main pilot will run for 4 months. Hopefully this will provide us a lot of insight in how this platform actually works, how we can apply it in actual environments. The pilots will be focused around 5 use cases, where we have 1 use case which is actually response on detected ongoing attack, and 4 use cases which are more like discovery new vulnerable assets, response on discovery of system configuration change, deployment of new systems and infrastructure, and also new cyber threat intelligence, which is actually, I think, the subject of today. DGA detection will go into this use case. So this was a short introduction. Of course, there's much more to tell, but like Richard says, we have the website, we have a LinkedIn group, we also are present on Twitter, and we have had several webinars already which were recorded and available on our website. So thank you.
Okay, so quick. So I'll start the webinar with an overview of what DGAs are, from the perspective also of Shadow Server and our contribution to this project, and also the testing of various tools that have been developed. Just a few words about Shadow Server. Shadow Server collects a lot of data, essentially focused on collecting data of malicious activity of all types, scans. We scan the internet over 50 times per day. We sinkhole botnets, over 5 million bots seen every day. We operate essentially thousands of honeypots worldwide. We collect a lot of malware. We index all the SSL certificates we can lay our hands on. About they're like many millions, I think 50-60 million per day for a collection of over 40 billion certificates. And we share all the data we collect with national certs and organizations, and over 6,000 organizations worldwide, and also aid law enforcement in various usually malware-related botnet operations, takedown operations. For the purpose of the project, we are focused essentially on our sandbox as a kind of a view into the ground truth of the malware out there. Obviously, it's not necessarily the ground truth, but it's at least a step closer maybe than many other perspectives, as we have a repository of right now over 1.5 actually billion samples in our database, unique by hash, and we collect hundreds of thousands, sometimes even over 1 million unique malware samples every day. And we actually not just collect them, but we also execute them in a sandbox, both using bare metal and virtual environments. And hence we get to observe quite a lot of the new interesting stuff that comes in. And we collect the malware through a lot of our sensor systems, individual submissions, but also by essentially partnering with the industry, where we share samples with around 60 different entities, vendors, researchers around the world. So the things that are being done in regards to detecting DGA threats are very much focused on what's observed in the sandbox. So a quick overview of what DGAs actually are. So, well, criminals need to reliably control their malware and essentially establish botnet command and control channels. And in the past, it was like relatively easy to block static IP addresses that the original botnets used, but it's much harder to block domain names than IP addresses. And essentially, this is what the botnet operators that utilize DGAs actually employ, where they generate thousands of domains every day that can be used to control their bots. But of course, they don't use all these domains to control their bots, but just are very selective in how many they use. And it's the defenders that then have to be concerned about how they actually go about identifying which domain name is actually in use for command and control, and how to block all of these domains. And a lot of things make it difficult to actually fight these kinds of botnets. One of the things essentially is the fragmentation of DNS industry across the world. Every registry and registrar essentially they operate under their own different ways and react differently to attempts to take down malicious infrastructure that's hosted via their domain names. So essentially, as what I said, criminal botnet operators only have to register one C2 domain in one TLD to retain control of their botnet and build the botnet resilience. Defenders, law enforcement have to register block C's all possible DGA domains in every TLD every day to prevent the attacks. And this is all achieved through domain generation algorithms, which essentially are like pseudo-random generators of domains that look random, but in reality follow a certain algorithm to generate a domain every day or potentially every month, depending on how the algorithm is set. So DGAs essentially offer an asymmetric advantage to criminals, where you had like where you have a kind of like a hydra that has multiple heads, and when you as a defender try to cut down the head, two heads or more grow in their place. So these threats are usually pretty hard to take down, and we see examples of botnets even today. Well, over like maybe over a decade since DGAs were first introduced, still using this method and still developing ways to build resilience using DGAs. So these are example DGA domains. Essentially, this is from an early CryptoLocker and early ransomware that has grown so prevalent today. So a DGA algorithm essentially can look like a random string with different registered in different TLDs. It looks random, but it's not really random. There is an algorithm behind it, so it's actually possible to set and predict what a domain will look like in a given if we actually reverse engineer the algorithm that is being used. And this threat is still, as I mentioned, relevant today. That was an older example from 2014, but even today, this method is being used, so it continues to be of relevance. FluBot is an example, essentially Android banking malware that is very active throughout Europe this year, and which has caused quite a lot of damage within the EU, and also outside, recently expanded in the last few months also to Australia, and possibly will expand to other areas of the world. So again, as we see, these are example of FluBot, 8 different DGA seeds. So same algorithm being used for FluBot, but different seeds for different groups that operate the malware. And here we see example domains registered in .ru, .su, .cn, .com TLDs. And again, as you see, the actual domain names generated, they don't really look much different from what has been used also in the past by other DGA algorithms. Well, this just shows that even the old methods actually do work, although in many cases operators of botnets also use words instead of just letter-based word-based DGAs instead of just letter-based DGAs to make it more difficult to detect usage of encodings of the DGA domains. So this is just to show you some overview of current FluBot infections around the world. As you see, mostly Europe being targeted, but increasingly the rest of the world, Australia since August. And at a given point in time, we observe through our own sinkholes, so we actually register these DGA domains, 20 to 40,000 infected machines worldwide. So the threat is real. And this is how FluBot looks. Yes, a couple of days ago on the 26th, most infections, Spain, Germany, Australia, but also many other places in Europe. And as we see also, the US, I guess, is also possibly going to be more region of interest as well. So how do we tackle the DGA malware botnet problem from the shadow server perspective and the SOCCRATES perspective? Well, we would want to be aware of all DGAs out there, so and detect new ones. So one way of doing it is is listed here, essentially step by step. We can collect all the malware in the world today, execute the malware samples in our sandbox, study DNS traffic patterns, classify behavior, identify potential new DGA-like domains that may be current CT domains, reverse engineer the malware, then forward predict future DGA domains based on the reverse malware algorithm, register 1% of all known DGA domains to sample command and control traffic, and then try to block seize all current and future command and control domains with the intent of disrupting criminal controlled botnets. So we have done this in the past with Avalanche, for instance, where we actually took over or blocked 800,000 domains in a couple of days. So it is possible. It's not just hypothetical. So yeah, so for the purpose of this project, we already analyzed millions of sandbox runs of 1.5 billion samples, as mentioned. We already do work with partners to identify botnet CAs. And having access to our DNS malware traffic in the sandbox, we can explicitly exclude all known DNS traffic from the traffic we see in the sandbox. We isolate the remaining new DNS traffic, and we can identify new command and control domains, and as well as DGA-like traffic and the malware samples that cause it. And then we can provide the malware samples to reverse engineer and add to known DGA collections, which is how we collaborate in this project, but also with Fraunhofer DGA archive. And we repeat this process, essentially rinse and repeat all the time. And the question in Socrates was really, can we use machine learning, deep learning methods to aid this entire workflow? So how do these DGAs look like on a typical random day? So yesterday, these are some stats, 95 different reverse engineered DGAs that we are aware of, a shadow server, 853 different forward predicted DGA and seeds, and nearly 500,000 unique DGA command and control domains out there. And we as shadow server track all these all the time. So from a defender point of view, if we wanted to actually block all these threats, some of them are dead, but some, as I showed, are still alive, then we would have to register all the domains in use. And if we estimate $10 per domain for 1 year, it is simply uneconomic from our perspective or any perspective to actually register 100% of potential DGAs or even sample a percentage of them. So that is a real problem for the defenders, and we work around it in multiple ways. We have a registrar called Roller, which has agreements with registries and registrars worldwide where we can actually register domains for free or at a bit of discount. But otherwise, it usually needs a big consortia of entities to attempt takedown of these DGA-related threats. So, example DGA family stats. This is actually all the known DGA malware out there that we can lay our hands on. So you can more or less see how different families employ different amounts of essentially DGA domains generated per day, from essentially tens of thousands, like from banking trojans like Timba, to just a few in case of other threats, maybe to stay a bit under the radar. But the range is very varied, and as you'll find out in a later talk by Rina, this also influences how well we're actually able to train machine learning algorithms to be able to detect these domains. So our objective, and as a way of introduction to Irina's talk on the actual technical details of our DGA detection mechanisms. Our objective is really to be able to distinguish DGA domains in traffic flows from normal domains and automatically classify these domains into malware families of known versus unknown, but also essentially the family names themselves. And most importantly, for our purpose, we need a solution to run at a large scale that's able to cope with all the data we collect at shadow server. So essentially deal with hundreds of thousands, millions of queries on a given day. So Irina will tell in more detail how we approach that. So essentially, if we go back to the hypothetical step-by-step of what we are trying to do as shadow server, you can see here that this is the step here where we actually try to help the analyst. These two steps, we're going to study DNS traffic, classify behavior, and identify potential new DGA-like domains that are in use.
Yes. In SAPPAN, DGA detection is a use case which we investigate. And here we took the research-driven approach. So we already published 6 peer-reviewed papers solely on DGA detection, and the 7th paper is currently under review. But we don't only focus on research. We actually have a great focus that our research finds application in the real world. And there we ensure that our classifiers are real-time capable and scalable. And we also put integration efforts such that our research finds integration into existing security information and event management solutions. Here on the right side, you can see a word cloud, and it contains various aspects we have been researching. And in the next few minutes, I will try to cover the big aspects or the interesting aspects in 1 or 2 slides each. So in SAPPAN, we started with DGA binary classification. That is to say, here we try to separate benign from malicious domains. And for this purpose, we proposed a residual neural network-based DGA classifier. And this classifier introduces skip connections. You can see it here, which ease the training and counteracts the vanishing gradient problem. We did a comparative study with several state-of-the-art classifiers, and there we could show that our classifier yields in a reduction in the false positive rate. And here we also investigated 2 different properties. The one property was whether the classifier generalizes well to different networks. That is to say, we train one classifier on real-world traffic from one organization and then evaluate it in a different network. And here we could show that our classifier generalizes well and thus can be outsourced as a service, for instance. And the other property we investigated was the time robustness of the classifier. Here we took real-world data or the real-world traffic from one point in time and then evaluated the classifier after 17 months. And here we have shown that the classifier is also time robust. The false positive rate, of course, increases slightly, and but still in a manageable way. And of course, if you want to have the lowest false positive rate, you should, of course, do frequent retraining. And as I said, we ensure that the classifiers are real-time capable and scalable. We did a real-world test in which we classified 1 month recording of a very large network, and it was real-time capable. We then continued with the DGA Multiclass Classification problem, which tries to attribute the domain names to either the benign class, which is located here at the top corner, or to the actual DGA that generated a specific domain name. And here we also proposed a residual neural network classifier, but this time the classifier is more complex. It is built up of 11 residual blocks. And we did also a comparative study of the state-of-the-art and could show that our classifier requires 30% less training time, and we could also improve the performance of the state-of-the-art by over 5% at macro F1 score, which means that even though it seems to be a rather low improvement, a macro F1 score increase of 5% states that we can detect several classes with very high confidence that the other state-of-the-art classifiers cannot detect. So here on the right side, you see a confusion matrix, which can show the performance of the classifier. And on the y-axis, you see the true label, which is either benign or 1 DGA. And on the x-axis, you can see the predicted label of the classifier for a given sample or for given samples. And a perfect classifier will yield an identity matrix, so an identity of black boxes on the diagonal. And you can see that the classifier detects a lot of DGAs with very high confidence. You can see some outliers, for instance, here the DNS benchmark, but this, for instance, is caused by the low amount of training samples. So we performed a 5-fold cross-validation, and we got data from DG Archive, and there it contained only 5 samples for DNS benchmark, and thus we train in every fold on 4 samples and classify a single sample. And if we classify this single sample wrong, the whole classification score degrades to 0 for that specific class. Yeah, and of course, we also ensured the real-time capability and scalability of the classifier. And yeah, the 2 classifiers I have shown you now are deep learning based, and of course, they heavily depend on the used training data. And as I've mentioned with DNS benchmark, the sample distribution of the DGA classes is heavily imbalanced, so of the samples of the classes is heavily imbalanced. And thus the question arises whether it is beneficial to include underrepresented DGAs at all for the binary and for the multi-class classification task. We investigated this problem in SAPPAN, and here we had a look whether or what's the effect on the overall classification performance of a classifier if we include underrepresented DGAs in the training process, and also on the ability to detect or attribute samples of underrepresented DGAs. We did a comprehensive study, and here we showed that both classification tasks benefit of including samples of weakly represented DGAs. For the binary classification task, we could improve its detection performance by over 10%. And for the multi-class classification problem, we could show that for 22 out of 46 DGAs, which were in the group of the weakly represented classes, for these classes, we achieved an F1 score of over 90%, and for 11 classes, even an F1 score for over 99%, only by including these samples. What's very important is that the classification performance of the classifier did not get worse for the well-represented classes. On the other hand, if you would actually let the well-represented DGAs out of the training, multi-class classifier would still need to classify those samples in a real-world application, right? And here you can see again the confusion matrix, but this time we did an experiment in which we trained the classifier on well-represented samples, or samples of the DGAs which are in the well-represented group, and we classified samples of the weakly represented group. And as you can see here, the samples are distributed over many malicious classes. But what you also can see is that the out-of-distribution samples, a huge fraction of them are actually attributed to the benign class. This means that these samples would be missed by an intrusion detection system. And here, for instance, the DGA could obtain a valid IP address for the C2 server and start to exfiltrate data or participate in any malicious action. Thus, in SAPPAN, we concluded that it's very important to include weakly represented DGAs to a training process. The classifiers which I presented now were deep learning based, and even though they achieve very promising performances, they behave like black boxes. And thus it's difficult to evaluate the line of reasoning, and this results in a lack of confidence. And this is maybe one point why Security Operations Center analysts would not be happy to use them, because they can't actually argue why a classifier classified a sample either benign or malicious, for instance. And in SAPPAN, we developed 2 approaches to counteract this issue. The first approach is based on a visual analytics system, in which we try to provide understandable interpretations for predictions of deep learning classifiers. And I don't want to go into much detail here, but we actually, the main idea is that we cluster activations of the model's neurons, and then we leverage decision trees in order to explain the clusters. The second approach is by using a classifier which is explainable by design. For this purpose, we proposed a feature-based classifier which we called explain. It is based on random forests, and it is competitive and contextless. Again, on the right side, you can see a confusion matrix, but this time it is combined with the deep learning-based approach we proposed earlier. And the upper left part is the classification score for the explain classifier, the feature-based approach, and the lower right part is the deep learning classifier based on the resilient neural network. And what is interesting is that the deep learning classifier seems to learn very similar features as we have defined for the feature-based approach. In total, we studied 136 context-less features, 42 of which we gathered from related work, and 94 were newly developed. And these features can be categorized broadly into 3 categories. The first category is linguistic features, which, for instance, investigate whether the domain name contains numbers or compute the vowel ratio. Another group is structural features, which is, for instance, the domain length. And a third group is statistical features, which calculates the frequency distribution for certain n-grams or the entropy. And again, here we also compared the classifier with the state of the art, which were the deep learning based approaches, and we could ensure that this classifier is also real-time capable. Another big point in SAPPAN is the intelligence sharing, which is also part of the acronym SAPPAN. And here we had to discover how to improve detection by collaboration, because a classifier can, of course, learn more by sharing private sensitive data. But the problem here is that the models which use this training data are heavily influenced by this training data, and the models can leak sensitive information, for instance, if you attack them with membership inference attacks. And of course, direct sharing of this sensitive data just leaks this information, of course. For instance, you could recover like browser histories of employees of our organization which has this data, for instance. And in SAPPAN, we improved the generalization and performance by sharing intelligence at different stages of model training. And the first naive approach would be raw data sharing. Here we applied several approaches for in order to not leak private information, for instance, applying Bloom filters and so on. Another approach for collaborative machine learning would be ensemble classification, which every organization would participate in collaborative machine learning, trains an own classifier, and these classifiers are then combined either by majority voting, for instance, or by averaging the confidence scores, and thereby you get like a collaborative machine learning model. A different approach we implemented in SAPPAN is feature extractor sharing. Here we do not share the whole model, but rather only a part of it, to which we refer as the feature extractor of a deep learning model. And the main idea here is that by sharing less of a model, we leak less information, sensitive information. And 2 other approaches are applicable during the training of a collaborative machine learning model. And here we use federated learning, in which we share the updates to a global model. And also we investigate the teacher-student learning, where a student is trained by the predictions of teacher models. We did an empirical study which showed that feature extractor sharing and federated learning perform best for DGA detection, and we could show that we can actually significantly reduce the false positive rate by up to 50% compared to single-party approaches. Another thing we examined is that the reduction in false positive rate correlates actually with the increasing number of parties, which actually shows that collaboration for DGA detection is possible and beneficial and working actually. And we did already a privacy utility trade-off study. As I said, sharing intelligence has always the problem of sensitive information leakage. And here we could show that for the federated learning approach, we can actually do private information sharing with a reasonable overhead. Another thing in SAPPAN is that we tried to propose classifier which can be used for privacy preserving classification as a service. And here the problem is that, as I said, for well-performing classifiers, real-world training data is used, which is not always available. And also, for instance, what's the question? What's about resource constraint devices? For instance, if you want to do like DGA detection on a phone, for instance. And here, of course, if you send a data item, you don't want to send it in plain, as the model provider would know which website you want to visit, and also the calculations done here should not be leaked to the client, as it may leak privacy critical information of the training data. And there are already proposed privacy preserving ML frameworks.
I'm sorry, Arthur, I no longer hear you.
Single classification. Of course, this is the worst case I've written here, but naively, this is not easily possible. So we did a comprehensive study.
Arthur, just like last 30 seconds or so, like we couldn't hear you. So if you can just go again from the problem.
Okay. Okay. The problem in SAPPAN. So you hear me now, well, right?
Yes. Now
okay.
we can.
Yeah, you're here now. Yeah.
Okay. So the problem is here that real-world training data is mandatory for well-performing classifiers, and this is not always available for everyone. And also the question here is, what's about resource constrained devices if you want to do like DGA detection on mobile phones, for instance? And if you do classification as a service, you usually provide the data item to the model provider, and the model provider then provides you with the prediction. And here, of course, you can't send the data item unencrypted, because the model provider would know which website you want to visit. And also the calculations done by the model provider should not leak any information to the data owner. And existing privacy preserving ML frameworks were already proposed in related work, and we applied them naively to existing DGA detection classifiers. And there we could show that a single inference can cost up to additional 13 minutes inference latency. And for a single data item, you would have to transfer like 234 gigabytes of communication for a single inference. And this is, of course, not feasible. And this is why we did a comprehensive study, which included several homomorphic encryption-based approaches and secret sharing-based approaches to secure multi-party computation. And we proposed several model simplification in which we actually could reduce the inference latency by up to 95%, and also the communication complexity by up to 97%. And this simplification leads to an accuracy penalty of less than 0.17%. Of course, the numbers I have mentioned here are worst case numbers, and if you reduce the average cases, you come to inference latency of several seconds or even under 1 second, but still this is not real world applicable. You need faster classification performance. And this is why this is still future work, and it requires still future work to make the privacy preserving classification as a service feasible for DGA detection. And yes, I will now present some current and future work. And of course, especially deep learning classifiers seem to be susceptible against adversarial attacks. And we did a preliminary evaluation, which we showed that NX classifiers, that is to say, classifiers that are trained on the domain names which are included in non-resolving domain responses, are more robust against adversarial attacks proposed in related work. Why should you use NX classifiers? The reason for this is that if you classify the NX traffic, you can actually detect DGAs or infected hosts before the DGAs or the malware is commanded to partake in any malicious action. And also the order of magnitude of the NX traffic is less than full resolving traffic by 1 order of magnitude. And of course, what is part of future work, we currently use different adversarial machine learning techniques to improve the robustness, and we will assess this also in a bigger study. Another thing is that we try to detect new DGAs. We already did one real-world experiment in which we detected 6 unknown DGAs and 1 unknown bimetal seed, which you can see in the figure, in the bottom of the figure. But what's the goal of this research direction is that we want to propose an adaptive system which can detect new DGAs. And lastly, we want to actually detect active CNCs of unresolving traffic. This is quite new, and we are currently researching it. And the main goal of all our study would be to combine all research into a single detection system, and also to ensure that everything is real-world applicable and real-time capable. This was a quick summary of all the research directions we took in SAPPAN, and now I will shortly go over the impact which is caused by our research. So of course we have a research impact. We improved the state of the art in various aspects. We published already 6 papers on DGA detection. Also the 7 papers are currently under review. And we published our research open source. So for instance, the binary and multiclass resonance-based DGA detection models architectures are publicly known, and you could actually use them in your own classification pipeline, for instance. And also the feature-based approach, we published it on GitLab. You can have a look on the source code. And there we published everything which includes feature selection, hyperparameter optimization, also the whole pipeline. And we also published the different configurations which you could use for classification. As I've said, we studied 136 features, but actually not all of them are actually needed for classification. For instance, the very feasible classifier which achieves state-of-the-art performance requires only 28 features. And lastly, of course, the developed classifiers are real-world applicable. Feel free to try it out. Explain is also very well documented. And there we also explain every feature in detail. And further, we put integration efforts of our research, and we integrated it already in a ZM solution. Here you can see a small excerpt of this tool. And here our goal is to facilitate the work of security operations center analysts. So of course, if you use our classifiers, you get the improvement of detection performance over the state of the art, and thereby you actually reduce the false positives. And of course, to ease the work of a security operations center analyst when he is, for instance, trying to verifying false positives or false negatives, our research tries to provide explanations for these predictions of the classifiers. Yeah, with that, I would like to thank you for your attention.
Thank you. So thank you, Richard. So I'm Irina, and I'm going to present our work on the DGA detection in SOCCRATES. So it will be a somewhat briefer presentation than the one of Arthur, because I will focus mostly on the pipeline looks and basically how we integrated some of the things. And this is my very small agenda for today, because I first discussed what's our vision in SOCCRATES concerning DGA detection. I will briefly mention how machine learning is used for detecting DGAs in practice nowadays. Number 3 marks how we've used a very specific type of neural network to detect DGAs. And then we'll have a look at the tool itself and some of the results. And there will also be a demo at the end. In SOCCRATES, we've been, let's say, very integration driven, because our approach, after discussing with Piotr at Shadow Server about the issues there, was mostly to try to provide as fast as possible a tool that works at scale and improve the machine learning model afterwards. So we was basically first focus a lot of effort on deployment and making sure that everything works in the environment, and then we've kept refining the models on the go. So as mentioned by Reiner in the very beginning, Shadow Server is basically one of the pilot sites of the SOCCRATES project, and there we have some KPIs that we need to meet, and a lot of them relate to either identifying new seeds of malware families or clustering correctly malware, identifying new signatures and things like that, and in the end also making sure that the API and that the tools that we develop are used by a sufficient number of partners. So all of these sort of supported this approach of, let's say software integration first and then refining machine learning second. The way we structured the approach was, when a new domain comes in, we first want to know, is it DGA or not? And for that, we basically do this binary classification. We apply machine learning that can either say, which one of the two classes it is. And depending on the outcome, this domain name can investigate it further and see, does it belong to a known malware family? And that we can basically do with some multi-class classification by, instead of saying, is it a DGA or not, being, is it a benign domain or is it one of these 85 plus families that we know? And as an additional step from there, if the response is either clear, if it's let's say established malware family, we cluster domains to see if it's a new seed, if we recognize it at all. And if the response from the multi-class classification is inconclusive, we basically try other approaches to see if we still find matches with any of the let's say domains we've seen so far. And the clustering part I will not discuss today because this is still quite a work in progress. But on top of all the tools that we've been doing, we're also looking at one-shot and few-shot learning. This is carried out by our partners at AIT. We're also active on this task in the project. And there we're trying to see whether with a few very good examples, if we can find basically DGAs from some of the known malware families. So this is a bit the thinking behind the tools that we made. Now, if you scan the literature on machine learning for DGA detection, you come across two approaches. And the first one is so-called feature-based. It's basically the case when you use the data that you have concerning your domain name and the DNS data to create features that are relevant for identifying different domains. And these approaches include basically this random forest, support vector machines, multi-perceptrons, and so forth. And the advantage of these methods is that they are explainable, let's say, by design, because you will know which features are more important or not. But the disadvantage is that, of course, creating these features costs time and you need proper data storage, and it's basically an intensive process. And then on the other hand is this, let's say, feature-less approach where you can just use the domain name, so just the string as it is, encode it to some numerical values or one-hot encoding, pretty much standard approaches, and feed that into a neural network. And this has been a bit our preferred choice because even though it is, let's say, more black box and less explainable, it does perform slightly better in our setting. And it was, let's say, less computationally intensive because we didn't have to do all those pre-processing steps. So this is what we went for a feature-less approach. The choice that we made for when we scanned, let's say, the realm of neural networks, we came across something called temporal convolutional network. This is basically a specific type of convolutional network. It has been shown in some recent studies to basically outperform other sequence models like long short-term memory networks and gated recurrent units and things like that on a lot of sequence modeling tasks. And this you'll be able to find in this paper that's on the slide. And what makes this temporal convolutional network so special is that they employ dilated convolutions. So if you look at this diagram, you see here on like the input and the residual block and the last layer, this is how the whole neural network looks like. And then if you zoom into a residual block, you basically see two dilated convolutions and then basically a skip connection that is also used in the SAPPAN network. And these dilated convolutions basically allow you to slide the convolution filter not on all the inputs, but only of some of them. So you can skip different inputs, and that basically gives you the chance to control the receptive field. So basically the amount of inputs that you actually use for learning, that becomes more flexible. You can make different choices in there. And that has been something that appealed to me when I chose this network. And it has a bunch of other advantages because it's easy to parallelize in contrast with the LSTMs, these kind of recurrent networks. It does require less memory when you train the model, because in an LSTM, you would normally have, if you're at a certain basically node, you would have to wait for all its predecessors to be computed and only then compute its value. That's not the case for this kind of convolutional networks. And because the backpropagation path is also different, they don't suffer from the problem of exploding the gradients and vanishing gradients. So yeah, these have been some of the reasons why we made a specific choice. And the fact that nobody looked at it before was also appealing, because we were curious on how we would do it. What we've done with it was first this binary classification, so see if a domain, if we feed it through, is it a benign domain or a DGA? We used data from from Shadow Server. We basically created a training set which pretty much resembled their daily intake of domains. So that's 50-50 in terms of occurrence of classes. So it has 50% benign domains and 50% malicious. And then we tested on a very large amount of data, which was about 30% benign, 70% malicious. And that 70% comes from 78 known malware families. So we had quite a lot of faulted with that. If you look on the right side, there's like this blue diagram. This is how you can imagine the workflow of what the network actually does. So you have a domain coming in, and in the beginning, there'll be a small pre-processing step that's applied. And in that step, the top level domain is removed. So in this case, the .com will be shipped out. And then this, basically the letters and the symbols eventually in the domain name are encoded to some numbers. And then the domain is padded at the end with a bunch of zeros, because for a neural network, all the inputs need to have the same length. And as many domains do not have the same length, we basically establish like a maximum length, and then we feed everything to zero with zeros at the end, such that everything matches. And then once this numerical encoding has been done, it's being fed to the pre-trained neural networks, which are waiting in a repository somewhere. And then the label comes out, and it can be either benign or DGA. And this whole, let's say, blue diagram, the software that's behind it, this you can use as a Python package. You can use it locally through a command line interface, and you can also employ it remotely to basically classify in parallel different data coming from different servers, let's say. So this I'll show you in a minute in the demo. But first, if we look at some of the results, so what we've done to, let's say, evaluate this formally was compare this temporal conversion network of ours with a very, let's say, popular network, which was the LSTM introduced by Endgame in 2016. And we basically did this 5-fold cross-validation, and we took the average of the different metrics. And you see here the two confusion matrices. And what it's important to see is that regardless of which of the 4 boxes you look, the TCN basically performs better. It has an accuracy of about 96%. There is still a significant amount of false negatives and false positives, but keep in mind that this is a very large test data set, so it has 3 million domain. So in practice, these numbers may not be as severe as they are shown in this example. So now we can move on to the demo part. And I would like to show it here. So it's basically pre-recorded a nice demo in which I've employed this DGA Detective live to classify subdomains. So I will play it for you now.
To use the DGA Detective via the command line, we have opened here a Linux terminal. By typing dgad-help, we can see the information about the different arguments of this command. We can pass as input a list of domains or a CSV file, we can select the machine learning model to be used, and we can activate the quiet option in the case when we wish to display no output in the terminal. I'll first classify a small list of domains. For example, europa.eu and these two randomly generated domains. The DGA Detective outputs to the terminal the classification result. So we see that europa.eu was classified as an OK domain, and the other two as DGAs. I can also pass a CSV file as input to the detective. Here we created an example file, domains-to-do.csv, which contains 2 domains. I now call the detective to classify the domains, and the resulting label will actually be added as an additional column to the CSV file. So you see here domain classification column. The DGA Detective offers a gRCP API to classify domains over the network. In this demo, we show how a server can handle requests from 4 different clients. We first start the gRCP server, and then we start the client. You can see right away that the server has started classifying different domains, and now we can add 3 more clients. What you see now is the server activity in the leftmost column and the 4 clients in the remaining columns. So each client generates 10,000 domains and sends them one by one to the server for classification. This demo shows that one server can easily handle many clients at once. The classification speed is very good. It's about 30 domains per second, and can easily be increased by deploying multiple DGA Detective servers in parallel.
So this was my demo. And now the good news is that this demo that I just made, you can replicate yourself with the instructions from our repository, because the DGA Detective has been open sourced a week ago. So if you go to this repository, you can basically employ it in your own setting and try to detect DGA domains from your own data, maybe. Make sure to check it out. And if you have any contributions or issues that we should look at, please do get in touch. And yeah, this brings me somewhat to the end of my presentation, which in short can be, let's say, summarized as we have a TCN network and we're very happy with it because it is a suitable solution for large-scale classification. It performs good enough. We are going to add soon the malware family classification option as well. So this is also going to be open source. And yeah, make sure to check out the tool and let me know if you have any questions.